Now let's look at Avogadro's law. Avogadro's law is a relationship between volume and number of moles of gas or number of gas molecules when we have constant pressure and temperature. And we see Avogadro's law in effect anytime we blow up a balloon. When we blow up a balloon, the pressure inside the balloon is going to be atmospheric pressure, and the temperature is going to be room temperature. But we increase the volume of the balloon by putting more gas molecules into it, or increasing the number of moles by blowing into it. Now let's look at the equation here, which represents Avogadro's law. V1 over N1 equals V2 over N2. This is another initial state and final state kind of situation where the pressure and temperature remain constant. We have an initial volume, an initial number of moles, and then we change either the volume or the number of moles, and then we can calculate our new volume or number of moles depending on what we've changed. Another way we can look at Avogadro's law is that if we have equal volumes of gases at the same pressure and temperature, they contain equal number of molecules. The gas doesn't matter. So if we have a 2-liter balloon filled with helium and a 2-liter balloon filled with oxygen, they both contain the same number of particles if they're both at the same temperature and pressure. Okay, so let's look at this example here. A 4.8 liter sample of helium gas contains 0.22 moles of helium. How many additional moles of helium must be added to obtain a volume of 6.4 liters? And we're going to assume constant pressure and constant temperature. So we know we're going to use Avogadro's law. We're just looking at the relationship between volume and moles, and our pressure and temperature are the constant, and we have an initial and a final situation. Whenever I use one of these gas law equations, I always write my equation at the top of my paper, and then I go ahead and list what I know and what I don't know. I'm given my initial volume in moles and my final volume, and then I need to calculate my final number of moles. So I'm just going to plug in V1 is 4.8 liters, and that's divided by N1, which is 0.22 moles. And that's equal to V2, which is 6.4 liters, over the number of moles that I'm solving for. So I'm going to go ahead and do this math right here, and I get 21.818 liters per mole, and that's equal to 6.4 liters divided by N. Now I'm just going to do some algebra here. I'm going to multiply both sides by N, which will cancel that N out. And then I'm going to divide both sides by 21.818 liters per mole, which will cancel this out. Divide this side by 21.818 liters per mole. And when I do my math, my liters are going to cancel out, my moles are going to come out top, so my units are all making sense. And my calculator tells me that, oops, sorry, I couldn't find my pen there. Didn't mean to make that big mark. We'll make that a decimal point. My calculator tells me 0.293 moles are required. Now, let's go back to our original question. And it doesn't ask us what the final number of moles are. It asks how many additional moles of helium must be added. So let's take a look. If our final number of moles needs to be 0.293 to get a volume of 6.4, and I originally had 0.22 moles in the balloon, then I had to add 0.073 moles to get my new volume. So this question has a little bit of an added twist in that you do have to solve for N2, but the problem isn't asking for N2, it's asking for the difference between our final number of moles and our original number of moles. It wants to know how many moles have to be added to get our new amount. Now let's look at one more example. If 1 mole of gas occupies 22, let me just highlight this. If 1 mole of gas occupies 22.4 liters at STP, what volume would 0.750 moles occupy? Well, you'll soon see that we could use the ideal gas law to calculate this because we are given a temperature and pressure. Standard temperature is 273 Kelvin or 0 degrees Celsius, and standard pressure is 1 atm. But it's a lot easier just to use Avogadro's law. We can use Avogadro's law because all we're varying is our volume and our number of moles. Our pressure, even though it's given to us, isn't changing, and our temperature, even though it's given to us, isn't changing. So I write my equation at the top, and then I go ahead and fill in what I know. I know my original volume is 22.4 liters. My original number of moles is 1. My second volume is what I'm looking for, and my second number of moles is 0.75. Now I'm expecting my volume to go down because if I have the same temperature and pressure and I decrease my number of molecules, then I should have a smaller volume. Let me use a different color pen here as I'm 22.4 filling in for V1, 22.4 liters divided by 1 mole, and that's going to be equal to our unknown divided by 0.75 moles. So if I simplify my left-hand side, I get 22.4 liters per mole. And what I'm going to do, let me just write the other side, V2 over 0.75 moles. I'm going to multiply both sides by 0.75 moles. Multiply both sides by 0.75 moles. So I'll cancel it out on my right-hand side. And my units will cancel out of moles. And I get 16.8 liters as my final answer. And that makes sense because I have decreased my original amount by to about 3/4 of it, and this is about 3/4 of 22.4, so my answer makes sense. After each problem, you always want to take the time to ask yourself, does it make sense? Okay,